As you can glean from the title, I'm a geophysicist, a seismologist, in fact. So my perspective on the Exodus narrative is going to be quite a bit different than biblical scholars or archaeologists. You might ask, what am I doing here? What's the seismologist have to do with the Exodus? And that's a good question. I ask myself the same thing. That's what I did last time I came here. And the reason I think I'm here is because most of the elements of the Exodus involve movements of water somehow, either when the Hebrews were leaving Egypt, being chased by the Pharaoh's chariots, or coming back across the Jordan River at the end of their trek. And movements of water is something that I know about. I spent many years running simulations of currents and floods and asteroid impacts and storm surge, you name it. You go to my YouTube site, there's like 90 movies about the movements of water in various situations. So I think my job here maybe is to try to quantify these beautiful pieces of art and maybe put some numbers on it. That's what I'm going to try to do. And to put some numbers on it, you have to look for some physical constraints from the Bible. And I'm hoping that people here can supply me some. What is a physical constraint? Mentions of numbers or durations or time or wind direction or even location is a physical constraint. If you're dealing with water, you might ask the question, I'm on dry land, did the water come up? Or if I'm on dry land, did the land go down and the water came in? You might say, what difference does it make? But if you're trying to make a physical relationship between this, it does make a big difference on exactly what happened. And maybe there are some clues deep in the Bible somewhere, or the narratives. In terms of a geophysical perspective, then there's a matter of sequence. Was this story, was it wet area first, it turned dry for a while, then got wet again? Or was it a dry area that got suddenly wet, then got dry again? Or was it a dry area that got permanently wet? Again, you might ask, what's the difference? But it does make a difference in terms of trying to interpret the story. Then there's the matter of duration. Would a few minutes of flooding be fine? That might be enough to get rid of Pharaoh's chariots. But if you're trying to move 10,000 people across a river, it's going to take a while, right? Maybe hours, maybe days, move 10,000 people across a river. So that's a different constraint, a different thing involved if you want to hold back the water for days versus minutes. So I'm going to zip through 6 different possibilities here. Each one gets about 3 minutes at a time, so you have to hold on tight. The first 5 have to do with the beginning of the Exodus, during the escape. And the bottom one has to do with after the trek was over, crossing back across the Jordan. So let's run through these. Earthquake tsunami, that's what you think of most people when they think of tsunamis. There's a big earthquake, there's shaking involved. The shaking doesn't make the tsunami, of course. It's a final offset of the fault that makes the tsunami. Offsets the bottom of the ocean, offsets the sea surface, and that offset spreads out as waves. So what earthquakes might be involved in the Exodus story? There are big sources of earthquakes in the Eastern Mediterranean, the Cyprus Arc and the Hellenic Arc, the 2 biggest. These are subduction zones where one part of the lithosphere is being pulled down into the mantle, much like it happens in Alaska or the coast of South America. These are capable of big earthquakes, maybe 8, something like that. So that's a plus and minus. Again, I'm always looking for pluses and minuses to these stories. What's the negative aspect? Well, they're kind of far away compared to their size. That's a negative aspect if you want a powerful wave, because it decays like square root of r, for instance. But let's run a simulation. That's what my role is here. There's one. This is a pretty big earthquake on the Hellenic Arc, magnitude 8 and more. And it might bring waves to the coast of Egypt, not huge ones, maybe 1 to 3 meters. Nothing, it's going to be like Tokyo style, the last big earthquake. And it's going to have several cycles, maybe 10 minutes, so that's going to be a duration constraint. There's some negative aspects I see. It's going to be a big earthquake. It's going to be felt all over the Eastern Mediterranean. And the tsunami will be felt as well, not just in Egypt. So you think there might be some archaeological or geological record of this wave other places. Could be there's an earthquake much closer to Egypt instead, but I don't know if there's any major faults close enough to make a local tsunami that could be relevant. One more drawback here. Is it listed here somewhere? You have to be very close to the shore. That's the big drawback, I think. A 1 or 2 meter tsunami might come in a few hundred meters, maybe a half a kilometer. So if you're dealing with a story with 10,000 people, they're going to have to be crowded on the beach more or less for this to be relevant. And that's a drawback, I think. Geographical constraint. What about volcanoes? That's a little lower maybe on the your perception of tsunamis. But volcanoes make waves in many ways, either a caldera collapse or a side of the volcano blows out. Everyone's probably familiar with Krakatoa, 1883, big volcanic explosion and a big wave. Just a decade ago, the sun of Krakatoa erupted and made a pretty good-sized tsunami. Maybe you remember that. How does that pertain to the Exodus narrative? Well, we do have a volcano, right? It's been mentioned several times over the years, today as well. Has some positive aspects. I'm always looking for positive and negatives. There was a volcano and it actually happened. That's a positive. That's better than hypothetical cases, right? It happened at the correct time, give or take a couple centuries, apparently, from what I hear. That's another positive. There are many ways you can model a tsunami from a volcano. You can have a piston collapse, a flank collapse, pyroclastic flow into the ocean. Simplest way is just put a bomb there and set it off. So here I put a 300 megaton explosion there. It's pretty modest for Santorini, I think. And it can make pretty big waves, 100 meters right at the source, maybe 20 meters at the coast of Crete. We know the Minoan civilization had a hard time with this wave, right? It knocked out their military and their harbors, and the whole civilization collapsed because of this. That's the thought. What happens when it gets all the way over to our area of interest? Take a look. It's a big wave at Crete, but it has some problems getting to Egypt, right? It has to feed through a couple little holes between some of the islands there. Anytime you squeeze through a hole, the wave spreads out again and cuts the amplitude. So it might be 20, 30 meters in Crete, but maybe 4 or 5 down here. You're in a corner. Anytime you're in a corner, that's good for waves, turns out. Anytime you have a corner, the waves tend to amplify. So that's maybe a positive. The duration is tens of minutes, maybe a few hours perhaps. Negative aspects, again, it's going to be a basin-wide effect. Why wasn't it seen somewhere else? And again, if you're going to tie this to the Exodus escape, you have to be really close to shore. Again, maybe a kilometer or two. So that narrows your options. What about landslides? We heard this mentioned earlier today. When there's a landslide, the bottom of the ocean goes up and down. It draws the surface water up and down in a similar pattern, and waves get generated. How does that happen? The thinking here is that we're in the Nile Delta. It's constantly being bombarded by sediment flowing out of the river. Nile's constantly growing in its size. The stuff that comes down is very weak material, full of water. And it's not at all unusual for these deltas to collapse, either from earthquake shaking or just spontaneously. And here's the concept. You're sitting here one day in a landslide. You can see it here in some of the cross-section. And the material sloughs off into the deeper part of the sea. Happens all the time. Positive aspect, right? Let's see, it's written there. Very common, not so unusual. And you might ask, how come I don't see this big scar today? Well, the scar might be filled in by subsequent sedimentation. You'd have to use a penetrating radar or something to see any fossil structures. So those are two positives, I think. Another thing I like about it is it's very local. You don't need a basin-wide impact to have this happen. And the size of the thing, since it's close, can be bigger than the first two examples. In fact, it can be as big as you want. Make the landslide thicker and thicker and thicker, you get a bigger and bigger wave. And let's see, it satisfies some of these sequences that I talked about. You have dry land, there's dry land, temporary withdrawal, the red, and then wet, and then dry again eventually. So if that's necessary to fit into your story, then this is a possibility. And it comes in a little bit further, so you don't have to be quite next to the shore to have this to be relevant. And it can last hours. Land is very flat, it takes a long time to drain away. What about wind-blown surge? That's not really a tsunami. You know, when hurricanes come, you're always worried about storm surge. That's probably the biggest hazard of hurricanes, right? Most of the storm surge comes from wind. The pressure difference is only at maybe 10%. When you blow on the water, there's a traction on the surface that makes the water accelerate in the direction of the wind. It takes a long time for this to happen. You need a long, long wind that's very powerful. But it can blow water around, as we know. Here's an example of an onshore wind, 80 knots. And you can see the water banking up. I call it the bank-up angle. It's very tiny, 1/100th of a degree. But if you have a 100-kilometer of fetch, you can move it up 10 meters and more. So you can see it moving up. It's going to keep flooding the land as long as the wind blows, more or less. So you can be many kilometers inland for this thing to work. Kind of remove some of your geographical constraints. There's the bank-up angle, you can see. Highly exaggerated. It can last as long as you want. You want to go for several hours to get 10,000 people across? That's a plus, maybe. Negative aspect is this is a pretty strong wind. And you got to get 10,000 people to walk against a Category 1 hurricane? That seems a little doubtful to me, right? So that's kind of a negative aspect of this wind story. There's an offshore version of this. It blows the water away. That's kind of cool, huh? Suddenly wet land becomes dry. You can imagine people sneaking across there and getting by after a couple hours. And comes rushing back in and gets all the Egyptian guys floating around. We saw those paintings on the wall. Might take hours to float back in. That's all good. Another real positive here, you don't have to be at the ocean. You could be any of these inland lakes and have the same effect, right? If you get a strong wind, in fact, shallow lakes are even more prone to storm surge because they're shallower. So this thing could have happened at any of these little shallow lakes. That's a positive. Flash flood, this isn't discussed much, but that's one of my favorites, actually. We all hear about flash floods in the news. I think West Virginia had a big flood just a few days ago. Why do I like flash floods for this story? Basically, because they free you geographically. You can have a flash flood anywhere. Anywhere in this whole trek, you can have a flash flood. And these are some lines of the Exodus path that I got somewhere. But you can imagine a flash flood happening anywhere in this place and having a pretty powerful effect. I like it also because it doesn't have to be widespread. It could be a local thing. It doesn't involve the whole Mediterranean, Eastern Mediterranean. 3, they actually happen. Again, that's always great and beats something hypothetical. 1975, there was a flash flood much like this one. It created a delta in the Mediterranean that lasted for a decade or so. One aspect of flash floods, they're pretty short, minutes. So if you're trying to get 10,000 people across, you're not going to do it in a minute. So that might be a negative if that's your goal. But here it goes. I can see easily this group of people crossing up one of these dry arroyos, just getting across, and all the chariots are coming up this dry riverbed. Some rain up in the mountain somewhere, and whoosh, it's a big flush. There's all the chariots right there. And those are the people getting washed away in the things we just saw. To me, it's very, very reasonable to me. Only takes a few minutes and they're all gone. As I say, this one happens at the end of the trek. Supposedly, they were coming up on the east side of the Jordan. For what little I know about the story, coming up on the path on the left, across over north of Jericho and south of Adam, I think. Somewhere there, maybe. And the idea that there was some intervention to stop the flow. And we're going to look at that from a geophysical perspective. Just to jump ahead, I'm going to put a landslide dam up over there, so keep that in the back of your mind. What's involved from a geophysics perspective in this story? Jordan flow rate is probably the biggest one. Right now, it's a tiny little creek, I call it, from Pennsylvania. You step across in 5 steps. But it wasn't always that way. They've been sucking water out for the last 100 years or so. The suggestion is in 1900, it was about 50 times that rate. And, that's not big either. I'll get to that. So what was it at Exodus time? That's unknown, of course. Was it climate drier by 2, climate wetter by 2? I've heard both stories. Let's look into this. If you go to the end of Sea of Galilee, where the water drains out, it's a tiny little opening there. If you've ever been there, it's 10 meters, maybe 20 meters wide. As the water goes over the little breakage there and slope. You can calculate by using the so-called the Weir formula, W-I-E-R. It's been around for hundreds of years. You get the flow rate of a rectangular opening, given the width and the height of the water. Supposing it was 51 cubic meters, the historical rate, 10 meters wide, it'd be 1.5 meters of water going over. If it's 20 meters wide, it's less than 1 meter of water going over, so it's not a massive flow. Some people say that the rates maybe were way higher back then. I don't know. I think there's references to priests getting wet feet or something. Someone suggests it's a flood stage at the time. If it was a flood stage, I think they just would have waited a few weeks, right? But I don't know. But let's see. Let's suppose it was 10 times higher. Then the Sea of Galilee would have to be higher, right, to maintain that flow. In fact, it would have to be 3 to 5 meters higher than the current level. Now, I don't know if the Sea of Galilee fluctuates that much in elevation. I think the Crusader structures are built very close to the sea. They haven't changed much in 1,000 years. But there's probably experts there who know more about Sea of Galilee than me. But if you want loss of flow, you're going to have to accept a higher Sea of Galilee by meters. So that's one geophysical constraint. The other issue is how fast is water going if you want to cross. At the outlet, you can use the same formula to get about 3 meters per second of water going across. At the outlet, it's a narrow spot. Certainly you're going to pick a wider place to cross, no question about it. Why do you want to do that? The wider it is, the shallower the water and the slower it goes. So at the speed, the volume that I'm talking about, it's not a very impressive river even back then. 0.5 meter deep, 2 meters per second, maybe less. So as I think of this, to me it doesn't really need much innovation. You can just go across. I think of modern analogs. When American wagon trains came to California, they probably crossed 20 rivers that deep and didn't have any issues. More recently, the Rio Grande. Rio Grande flows 2 or 3 times the historical rate of the Jordan. And we saw 10,000 people come across from Mexico in the last few years. They didn't need any intervention. So it's a story from my perspective. But I have no problem. Maybe it did dry up. Let's try it. And as I alluded to earlier, let's put a landslide across. Several ways to block it. You could have an earthquake like this to block the flow for a while. In 1811, the whole Mississippi was blocked for a few days because of an earthquake, right? Or you can dump a landslide. That's probably the easiest way. The question is hold time. Hold time is the capacity of the reservoir you've created divided by the flow rate of the water in. And the capacity has to do with the basin shape and the dam height. Probably this landslide happened in a narrow place, that's my guess, the steepest walls. How much hold time is needed? If you're trying to get 10,000 people across, does that take an hour, or a day, or a week? I don't know if they had animals to get across or what. Maybe someone can enlighten me. So how big of a dam is needed? That's to get that hold time. I'm almost there. I also understand that after everyone crossed, they piled stones in the middle of the dry bed. I read that somewhere. That's got to take some time. So it couldn't be hours, it's probably a day and more. From a geophysical question, is the amount of material reasonable? And causes, we know there's lots of causes. There's an active earthquake zone. We just saw earthquake landslides in the previous talk. It could also be from a flash flood blocking the river, or an earthquake, as I mentioned. Plenty of possibilities. Where does simulation come in? It comes in to this hold time question. How big of a dam do I need? And I find of the simulation, the flow rate's not very high. 10 or 20 meter dam could hold the thing back for days and days. That's my contribution here, I think. It's a very modest dam. You're not going to need 100 feet high, 1,000 feet high. 10 meters, and that's plenty. So I think this is a quite plausible, even routine mechanism. We saw on the previous slide some examples from 1927. So I'm finished more or less. There we are. I don't know where or how or if water movements aided the escape of the Hebrews from Egypt to Israel, but it seems like there's at least some plausible mechanisms involved. Some are far-fetched, some are more likely, some are probably impossible. And the last thing I want to leave you with is that I take requests. If anybody out there has a famous water flow thing in the back of their head, talk to me. Maybe we can run up a quick simulation for you. Thank you very much.
What about combination?
What about what, sir?
A combination of...
Oh, you want an earthquake and a landslide and a tidal wave and a hailstorm? I don't know. Yeah. Well, maybe you could do that. You could have the earthquake cause a landslide. Yeah, the earthquake causes a tsunami and a landslide. You can do all kinds of cool stuff. Sure. You get landslides with earthquakes. They come in pairs. Yeah, sure.
You could simulate.
Sure. You want me to actually simulate the landslide?
A combination.
Maybe they have different time scales, different space scales. Makes it trickier. Sure, I can do it. Yeah, that's one of my concerns. If it was a basin-wide effect, why wasn't this seen in Jordan or someplace else? I don't know. Has there been evidence of earthquakes, tsunamis in the Mediterranean? Sure. I don't know about that time, but in historical, I'm a seismologist, so our record goes back 1850 or something. But sure, there's earthquake tsunamis in the Mediterranean, not too big, a meter or so maybe. And there's volcano landslides off Etna and different places that have volcano tsunamis. Yes. That's right. You found some evidence in wells or something? Was this the story?
No, we found.
Microphone.
Yeah, we used sediment cores and found a layer that looks like a tsunami layer because it had rip-up clasts, and it was a mixture of clay, pebbles, gastropods, and we dated it to 10,000 years ago to 9.2, which means that the sea level.
Sea level is a big issue. It's gone up a lot, so
It was
a lot of the sites are
lower.
underwater now.
And I think the run-up was estimated between 12 to 9 meters.
To be honest, I don't remember what the earthquake source I put there, but
So I think we used the door disturbance, which is a localized...
you had a big landslide.
Yep.
I've done so many sims I forget. Yeah, you had a big landslide, and it did make a big wave. You can make, from a landslide, you can make it almost as big as you want. Make the landslide thicker, right? So
Yep.
that's a plus with landslides. You just dial it up, and it's also close to shore usually. That's where it's steepest.
Delta today is very deep.
Sure. The topography is very different. Absolutely, positively. So all my sims are current topography.
So
Yeah, of course. You're right. That's absolutely true.
you can stimulate.
If someone can give me it, I'll simulate it. You need a digital elevation map from 3,000 years. Probably exists somewhere.
Satellite can take a picture.
They can't go back 3,000 years, but sure, that'd be fun. If you have something, if someone has an old DEM laying around, you could give it a run.
Do we have any other comments on that paper? How many people in the audience like tsunamis? Nobody? Oh, we're fascinated by them, right?
I have a comment.
Yeah, go ahead.
I was just going to say about the two things about the Sea of Galilee. There's a question about how its depth. We know that the harbors from the early Roman period and Byzantine period, when the sea has gone down, have been uncovered, and so it's more or less the level it was now in antiquity. And the other comment I was going to say is in terms of the flow of the Jordan River, the biblical text does say that it was the time in which the Jordan River overflows its banks, which is an important point as to why, whether or not it's historical or not, the point is that it's as big as it could have been in that time period. So it's not just its regular flow, but when Mount Hermon melts and brings as much water as possible to the Jordan River.
Yeah, I just, on the Thera explosion, that, I just wonder, it was a specific kind of volcanic collapse where the core collapsed and formed this incredibly sheer, deep caldera, which would act as a piston, basically. And I don't know how that relates to a 300 megaton explosion, but it is a very specific geological source for that tsunami. And I would like to know whether you could actually use that as the initiator in the model, because it must be easy to model that geologically.
Steve, I think that's a question for you.
Yeah, they call that like a piston source.
Yeah,
Piston in a-
yeah, but it's
really work.
it's very explosive in that I mean, when it hits the magma,
In the first few seconds.
yeah.
The piston might be developed later, much later on.
Just a comment for Chris about the Jordan River. That's highest in the spring. The Nile, on the other hand, is lowest in the spring. So this is having a very long river gives you that from a different rainfall area.